Hello everyone, my name is Ganchev and I am going to present to you the paper entitled Automatic Pulmonary Nodule Detection and Management System at the International Conference on Applied Mathematics and Computer Simulation. This work was done as part of a bilateral research project with colleagues from China led by Professor Zhanlin, who is the first co-author of this paper. My presentation includes 5 parts. After a short introduction, I am going to present to you the system architecture, then the system functional models, then the Internet of Things platform Emotion, on the top of which the presented system works, and finally the conclusion. Lung cancer ranks top among malignant tumors. It represents a major chronic disease that threatens the life and health of citizens. The 5-year survival rate of lung cancer patients could be improved if the number of diagnostic stages increases. Therefore, improving both the early diagnosis rate of cancer and the survival rate of patients is considered as an important goal and effort direction. Pulmonary nodules refer to focal, round, dense, glass or hybrid structures of various sizes, contours and shapes contained in lung images. A clinician can observe their presence and determine whether a nodule is a malignant one and whether follow-up treatment is required. However, doctors are limited in their physical ability. In this context, CAD systems have emerged which can not only lower the workload of doctors and increase the detection speed, but also can lower the rates of misdiagnosis. Building on previous research, a successful design and implementation of an automatic pulmonary nodule detection and management system operating on top of the IoT platform Emotion is showcased here for easy use by both physicians and patients. The architecture of the developed system is shown in this slide. The front end consists of PC front-end pages created by means of the Vue UE3 framework and the WeChat mini program interfaces employing the Tart3 framework. The backend utilizes the traditional combination of Spring Boot and MyBatis Plus based on Java, with security and permission framework being Shiro. For storing the system and user data, the open source database MySQL is utilized. In terms of mode of deployment, the Flux framework is adopted, and the storage of images and key documents is managed using the FastDFS high-performance distributed file system. To enhance the stability and performance of the system, Nginx is used for load balancing, which also allows for future upgrades and expansion. The overall system operation is depicted in this slide. When conducting pulmonary nodule detection, the front end sends images to the Spring Boot server, which stores the original images in FastDFS and records relevant data in the MySQL server to associate images with patient and physician information. The server decides on how the input images need to be processed based on their category. In case of CT images, the server calls the Flash server to send back the image address and uses the Python language to process the CT images stored at that address. After processing, the results are returned to the Spring Boot server, which stores them in FastDFS and records corresponding information in the MySQL database. Subsequently, the Spring Boot server asks the Flash server to invoke the relevant pulmonary nodule detection model. After detection is completed, the Spring Boot server records the relevant result files and image files. In guess mode, Upon receiving new images provided by unregistered users, the server, by default, only performs CT image processing and pulmonary nodule detection without data storage in order to save this space. However, the system administrator can configure the system to store data provided in guest mode as to expand the dataset used for model training. Finally, the Spring Boot server displays the detection results through the front-end interface and provides services for downloading the result files for users wishing to do so. This process aims to ensure efficient and accurate pulmonary nodule detection while considering data storage needs under different user modes. The login and registration module provides user login-related functionality, including logging or registration for both PC and mini program interfaces. On the login registration page, users need to enter their account password to complete the backend verification before logging into the system. If the verification fails, it displays an error message allowing the user to retrieve the password or enroll to the system. The mini-program login interface supports guest mode, which allows direct use of a low-precision version of the detection model. Registration on the mini-program site is limited to patients, while PC site registration allows the choice of a physician identity. The physician accounts require administrator approval before this can be used. The image preprocessing module is activated if users upload non-CT images. For instance, if the images are uploaded in a medical-specific image format such as DICOM or MHD, the system performs relevant preprocessing operation and stores the results in the file management system while also displaying this correspondingly on the page. The figure on the left-hand side of this slide shows the image upload operation interface, whereas the other figure illustrates an uploaded original image and the corresponding image after preprocessing. Images outputted by the image preprocessing module are inputted into the pulmonary nodule detection module, which selects corresponding neural network-based model depending on the user type. By default, guests and patients use the EFPN SSD model, while the physicians use the MFFN SSD model for pulmonary nodule detection. Administrators have the authority to modify these default configurations. The images outputted by the pulmonary nodule detection module are stored in the file management system, and the relevant information is returned to the Spring Boot server and recorded in the patient information table, providing data support for downloading detailed result information. The display page of this module is shown here. The sequence diagram of the pulmonary nodule detection module is illustrated in this slide. The information management module is designed specifically for system administrators and physicians, providing comprehensive information management capabilities. The administrator page presents detailed information including the work status and vacation status of physicians and the number of patients handled by each of them. Administrators can perform operations such as adding, deleting, modifying, and querying physician information, and in addition have the authority to review new physician registration accounts. Moreover, administrators can reassign the correspondence between physicians and patients, as well as can reset system default parameters and other functionalities. The administrator's operation interface is shown on this slide. The presented system operates on top of Emotion, which is a self-developed horizontal type IoT platform serving multiple IoT application domains. The main characteristics of this platform are the heterogeneity, the multi-service provision, the flexibility and easy expansion, the cloud-based structure, the openness, and the inexpensiveness. Emotion can serve multiple IoT areas as presented in this slide. The IoT platform Emotion consists of 7 tiers: sensor and actuator tier, middleware tier, cloud tier, communication tier, modeling and simulation tier, and client tier and service tier where the presented system operates. The generic communication architecture of Emotion is shown here. The IoT nodes communicate with the information center in the cloud via remote transfer units (RTUs) and communication gateways. Each RTU is equipped with a relevant communication module to reach the corresponding gateway over a wireless connection. This way, the information center can collect and analyze data from all deployed RTUs as to obtain respective comments, decisions, recommendations, or provide information for the services operating in the service tier and to applications operating in the client tier. And here I come to the conclusion. A self-developed automatic pulmonary nodule detection and management system has been presented, built on top of the IoT platform Emotion. The system architecture has been described, including its overall structure, functional modules, database schema, and model deployment. The designed and implemented system offers effective tools for physicians and patients to conduct preliminary diagnosis of lung diseases. This not only helps to alleviate the workload of physicians, but also aids in the early detection of potential pulmonary nodule-related health issues. It provides a more convenient way for physicians to systematically handle and cure their patients, while also providing the patients with more opportunities for follow-up treatment. Thank you for your attention. Please send any questions or comments you may have to my email address provided on the first slide.